ndapongolere kuku konganda kumeme konganda kutate konganda kusezi ndapongolere meme ondalimbirwa kuku meme ondapongolere kuku tate ondalimbirwa sezi konganda kumeme konganda kukuku konganda kutate ondapongolere sezi.
We begin chapter 3 talking about predicates and quantified statements. So the first thing we want to talk about, predicates. We have to define what we mean by this. So what I want to assume is the following. I want to create a universe. And I want to assume that the universe is a set and it's composed of a couple of people, Alice and Bob, Kathy and Dave. And if you're not familiar with these names, Alice is a woman, Bob is a man, Kathy is a woman, Dave is a man. And I'm going to come over here and I'm going to write a statement as follows. I'm going to say P of X is equal to the statement X is a woman. Now the thing to notice over here, this statement P of X, X is a woman, this is sometimes a true statement and it's sometimes a false statement. It all depends on which one of the values from my universe I substitute into the predicate. For example, if I were to come along here and I were to talk about P of Alice, that's equal to true. And if I were to talk about P of Bob, that would be equal to false. So we can say that a predicate is a statement, but it also has a variable involved in it. And the statement is true or false depending upon what value we replace for the variable. Now remember, the variable has to come from our universe over here. Now your book talks about what is called the truth set. So we can talk about the truth set of P of X. And in this situation here, it would be which one of these elements here make the predicate P of X true. And in this situation over here, it would be Alice and Kathy. So you will notice that this is a very different way of expressing things than what we had from chapter 2, where we were just talking about propositions. Propositions are really nice if you're only talking about a single entity. But when you want to talk about whole classes of things, then you have to resort to predicates. And we'll find that predicates are much more expressive than propositions. Let's assume that we have a universe. This is going to be quite big. We want to assume that everything is there. So when I say everything, that means all of the people. For example, you may recall from the last set, we had Alice and we had Bob. And there were lots of other things, but this also includes my printer. Okay, it includes your cell phone. and lots of other things here. We're going to see that frequently we need to talk about sets where we can't explicitly list every element in the set. So while this is a very informal way of stating it, I think the intent of it is clear. And now I want to suppose that I want to express something about everything in this set. So we'll go back to the Greeks, and let's consider the sentence, all men are mortal. Okay, now when I'm referring to men here, this includes women. I'm actually referring to human beings. Maybe I should rewrite it this way. All human beings are normal. So we can imagine a couple of things over here. First of all, we could imagine the following predicate. I could call it h of x. And I'm going to say that x is a human being. And we can also consider introducing another predicate here, and I'll call it m of x. And we'll say that that represents that x is mortal. Good. So now we have a new symbol here that we're going to introduce. It's called this. It looks like an upside down V. Sometimes people say this could be stated as for all. Some people also refer to this as the universal quantifier. And what I'm going to do now is I want to express the fact that all human beings are mortal. And I'm going to consider the following way to possibly say it. I come down here and I say for all x, okay, for all x, if x is a human being, then x is a mortal. Okay, this is an expression of this statement right over here. Sometimes people will write it this way, put some parentheses around it, and we'll also put a parentheses around that. It's not always necessary to do that when the meaning is clear, but this is a statement now where we are saying that all human beings are mortal. If you are a human being, then you are mortal. Let's consider statements of the form like this. All x are y. Okay, so an example of that, of course, would be that all men are mortal. Now, on the last slide, we said that the way that we would represent all men are mortal is we would say something like the following. We would say for all x, and we said, let's see, we had human x implies mortal x. Now, some people wonder, why did we use implication? Some people would claim that perhaps a better way to represent that statement would be this. For all x, h of x and m of x. Well, let's consider the following. You may recall in our previous slide, we had a universe We said the universe consisted of everything. In fact, it consisted of my printer, and it also consisted of your cell phone. Now, let's consider what would happen if we were to stick my printer, if we were to substitute it for X into this. So what we are asserting is that human, my printer, and mortal, my printer. Now, I think you will all agree that my printer is not human. I think you would also agree that my printer is not mortal. Now notice over here we have an and, so I'm anding together two statements that are false. So the conclusion is this is a false statement. But now if I come over here, and I have H of I was going to write my computer, if I write my printer, implies mortal my printer, we note the following. Well, again, it is certainly not the case that my printer is human, but notice over here we have this implication. And recall our rules about when implications are true. If the premise or the antecedent, this part right over here, if this is false, then this statement is still true. So if I come over here and I stick my printer in here, it's kind of a strange statement, but it's true. So I want to go back to the original statement that we made here. If I want to assert that all x are y, the logical connector that I want to use is implication, not and. You're making stronger statements here. This is a much more general statement over here than this one over here. Let's consider a different sentence now. Suppose I were to say to you, some Namibians are tall. Well, let's think about this for a moment. Let's draw a picture of the universe. So let's assume that everything in the universe is contained in this square. And again, this is Namibians and Angolans and South Africans. It also contains my computer and your cell phone. The whole universe is in here. Now, someplace over here, these are the Namibians. Okay, and we might even represent that with a predicate. We might come over here and say n of x is equal to the statement x is a Namibian. Now, someplace over here, this corresponds to all the tall people in the world. And again, we might express that as a predicate, and we could come over here and say t of x is equal to x is a tall person. Now, notice when we are saying that some Namibians are tall, we're actually referring to the people right in that area right over there, okay? Those are the tall Namibians right there. So those actually correspond to the elements in the universe that are in both of these sets. So we would come over here and we would say something like the following, and we're going to introduce a new symbol here. Now this symbol right over here has a name. It's called the existential quantifier. And when we're reading it, we read it as saying there exists. So the way to state this statement right over here is we are saying there exists an X such that X is a Namibian and X is tall. Okay, now notice what we're saying here is we say there exists an X. There may exist 2 of these or 3 of these or 500 of these. But the point that we want to make here is that when we want to make a statement like this, if we want to say some X or Y, we're going to use an existential quantifier, and we are going to use the logical symbol AND. Okay, remember that contrasts with when we want to make a statement like all X or Y, then we say for all X or for all whatever the variable is, and there is an implication over here. So this is called universal quantification. This is called existential quantification. We want to talk about negating statements that are universally quantified or existentially quantified. For example, consider the following. Suppose I were to just say to you that for all X, P of X. Okay, now remember what this is saying is that for all the X's in the universe, P of X is true. Now, suppose I were to say to you, this statement is false. Okay, what does that mean? Well, originally we thought that it was the case that for all X, P of X is true. If that's not a true statement, then that means that there exists an X such that not P of X. In the original statement where we didn't have the negation here, for all X, P of X is true, we're saying, gee, that's not true, that's false. Well, that means that somewhere in the universe there is an X, and it is the case that P of X is not true, or not P of X is true. So let's consider what this might look like. Suppose I were to say to you, all lions are nice. So we might come along and we might write something down like this. Lion X implies nice X. And all of a sudden somebody comes up to you and says, wait a second, that's just not a true statement. There are lions out there that aren't nice. So I want to negate this statement right over here. And I stick the negation in front. Now, according to the rule that we have just written here, this is equivalent to there exists an X. And now what I'm going to do is I'm going to negate the statement that is inside here. So I'm going to say not lion X implies nice X. Okay? But what I want to do is I want to play with this statement a little bit more. You may recall when we first learned about implication, we said A implies B is the same thing as saying not A or B. And what I'd like to do is I would actually like to rewrite the implication over here in this form right over here. So the statement that I've written over here is equivalent to saying there exists in X not, and I'm going to come over here and I'm going to say not lie in X or nice X. Okay, and notice what's going on here is I now have this negation over here, and what I want to do is I want to apply De Morgan's rule. Now you may remember originally De Morgan's rule said something like this: if you have not A or B, that's equal to not A and not B. But notice what we have over here is we actually have one of the terms is already negated. So what I want to do is I want to talk about not A or B. Again, by De Morgan's rule, that is going to give me A and not B. From here I went from A to not A. From here I'm going from not A to A. So now I finally come over here and I'm going to rewrite this statement. There exists an X, and it says lie in X and not nice X. And again, if you recall from the last slide when we talked about the existential quantifier and what statements it applies to, and notice we have an and here, this is saying some lions are not nice. So notice what we've shown here actually is that the negation of the sentence, all lions are nice, got us down over here to say some lions are not nice. Let's consider the negation of an existentially quantified statement. So if I were to come over here and say there exists an X such that P of X. Okay, now that is an existentially qualified statement. And suppose I were to tell you it's false. In other words, what this is asserting here is that there's at least one X that satisfies P of X. If I were to come over here and say, well, that's not true, what that's saying is that for all X, it is not the case that P of X is true. I guess there's an X missing there. Okay, let's consider that to a statement that we looked at before. You may recall we said that some Namibians are tall. So we had the case, we had the statement, we said there exists an X, that we had N of X and T of X. N of X represents the predicate that X is a Namibian. T of X represents the predicate that X is tall. And we're saying there exists an X that N of X and T of X. Okay, there's at least one Namibian that's tall. And we go out and we do a survey of Namibia and we find out, no, that is not true. So let's negate that statement there and see where it gets us. Now, according to our definition right up here, that is going to be equivalent to, for all X, not N of X and T of X. And now what I'm going to do over here is I'm going to apply De Morgan's rule over here, and I get that this is equivalent to And again, what I'm going to do now is I am going to use a rewrite rule over here. You may remember that A implies B is the same thing as saying not A or B. So from that, suppose I were to consider the following. Suppose I were to have not A or not B. Well, I think that you would see that that would be the equivalent to saying A implies not B. So what I'm going to do is I'm going to use this fact right here and rewrite this over here, and I get this is equivalent to, okay, and this is going to be and remember, this is the way that we see lots of our universally quantified statements. I have a for all x, and there's an implication. So what this statement is actually saying here is it's saying something like the following. Remember what the original statement over here was. This statement here this was saying some Namibians are tall. So what we've shown here is the negation of some Namibians are tall is all Namibians are not tall.